Okay, so today we start chapter 7. Chapter 7 is about ionic bonding. We will finish this before the final and take a test on this. This is fairly short. So about a week and a half for the next test. Yeah. So I said we finally know enough about atoms and their electrons to predict how things are going to behave, okay, and to see what kind of compounds we make. But our way of doing it by writing electron configurations gives us a whole bunch of things that we're not really concerned with most of, because we really only have to concern about some electrons. So we need to keep track of the electrons. And actually, not all of the electrons. We can be general about most of them. We need to be specific about the ones on the outer energy level. Because when two atoms go to interact, the parts that run into each other are the outsides. Atoms are superficial. They only care what's on the outside. You might have the heart of a noble gas, but you've got 3 electrons on the outside. And you're going to behave the way you do because you have 3 electrons on the outside. Because when another atom comes to interact with you, it's going to see those 3 electrons on the outside. And as you saw by doing that, those 3, and we've talked about them a bunch of times, those outside electrons are called valence electrons. And it says, mine didn't say, I didn't just say in the outer energy level, I said the S and P, but the S and P orbitals are where those electrons are going to be. Because the biggest number always goes in front of S and P in any electron configuration. Okay. The ones that aren't valence electrons, those are called the core electrons. And if you think about it, this was our basis for the shorthand. We were specific about the outside. The outside looks like this, but the inside looks like this noble gas. So the core electrons were the ones that we put in brackets as a noble gas. And then we were specific about the ones after that. Okay. So 2 kinds of electrons, valence electrons, the ones that do everything, core electrons, all they do is provide shielding. Okay. So, we just spent a whole unit on the periodic table, so we found that atoms in the same column have the same properties. That's why Mendeleev put them in the same column. But he didn't know why, but we do. We know why they have the same properties. They have the same properties because they look the same on the outside. That when an atom comes up to an atom in group 1A, group 1A is always going to be the noble gas before it, and then S1. So no matter what atom comes up, it sees 1 electron on the outside. And it's going to treat it based on the fact that it has 1 electron on the outside. Which means they have the same number of valence electrons. So see if you can notice the pattern for me. That in group 1A, they have 1 valence electron. In group 2A, they have 2 valence electrons, because that would be S1 and S2. Group 3A would be S2P1. That would be 3 valence electrons. Group 7 would be S2P5. That's 7 valence electrons. So to find out the number of valence electrons, just look at the group number. The ones followed by A's, because we're using the ones followed by A's, right? So 1A has 1. So for example, today on the bell work, I gave you calcium, and it was in 2A. So you should have said it has 2 valence electrons. Sense? I'm going pretty fast because this should all be refresher from the stuff you turned in just a minute ago. Right? So let's make sure everybody's on the same page. How many valence electrons does phosphorus have? First step, find it on the periodic table. How many valence electrons? Let's say it's group 5A. If you can't see the numbers, you can count. 1, 2, 3, 4, 5A. So 5A means it's got 5 valence electrons. Okay? So we need a way of talking about those valence electrons easily. And that's what electron dot diagrams do. I call them electron dot diagrams. Sometimes they're called Lewis dot diagrams because the scientist who figured out to do this, his last name was Lewis, Gilbert Lewis. He was doing this in the early 1910s, just after the electron was discovered. Okay? And all it is a way of keeping track of valence electrons. So on tonight's homework, just like on the thing you did before break, the tutorial, you're going to have to draw them. Okay? And it's really pretty easy. First, you write the symbol. I wrote a big X. There is no element X, but that's where the symbol would go. And then you put 1 dot for each valence electron. The only question is, where do you put them? Well, can you see that there's 8 dots? Okay. I don't want you to think of it as 8 dots. I want you to think of it as 4 pairs of dots. A pair on top, a pair on the bottom, a pair on the left, and a pair on the right. Because the only rule about where they go is they don't pair up until they have to. So you can start on any side. Doesn't matter which side you start on. The only rule is that until you get to the 5th one, there will not be a pair. Does that make sense? So let's do a few. Draw the electron dot diagram for nitrogen. First thing I do, find nitrogen on the periodic table. It's in group 5A, so it has 5 valence electrons. So first we write the symbol. And for nitrogen, that's a capital N. Be careful with your capital and lowercase letters. If it has two letters, the first one's capital, the second one's lowercase. Okay. Now I got to put in the dots. And where do they go? Well, one electron at a time. And the first one can go anywhere. I'll put it there. The second one can go anywhere except next to the first one. Third one can go anywhere except for the first two. The fourth one has to go on the fourth side. Now I'm at the fifth one, so they're forced to pair up. And that's the electron dot diagram for nitrogen. It's got 5 dots because it's got 5 valence electrons. I could have put the pair on any side. Doesn't matter which side I put that last one in. Pretty easy. Let's try a few. Let's do the electron dot diagram for sodium. Draw electron dot diagram for sodium. Well, I did half of it already. I wrote the symbol. How many dots? Well, Na is in group 1A, so it gets 1 dot. Where does that dot go? It doesn't matter. Go on any side. That's one possible answer. Could put it there just as well. Doesn't matter which side you put it on. Okay. How about Mg? How about magnesium? So magnesium, group 2A, 2 dots. First dot can go anywhere. Second dot can go anywhere except the same size of the first one. So you can put them on opposite sides, one on top, one on the left, one on top, one on the right. It doesn't matter. So let's see if you can do this one. This one, it matters where you put the dots, because there's only one correct answer, because you find carbon is in group 4A. So I put in 4 dots, and when I put in 4 dots, it doesn't matter where the first one goes. The second one just can't go next to that one. Third one can't go to the next to the first two, and the fourth one is stuck by itself. Need one on each side. Make sense? Oh, that was easy. O's in group 6A, S2P4, 6 valence electrons. So 1, 2, 3, 4. First I got to put one on each side, there's 4. And then I got to put in 2 more. It doesn't matter where they go. So I put 1 here and 1 there. Or I could have put 1 on each side. As long as I have 2 pairs and 2 unpaired. See if you could do this. Fluorine's a halogen. Halogen's group 7A. So 7 dots. Put 1 on each side to get to my 4. Got 3 more to go. make 3 pairs and 1 unpaired. Okay. So it's always 8 dots, but it's really 4 pairs. Does that work for any element? Any element. Okay. Noble gas, group 8A, 8 dots. There's only one way to do 8 dots correctly. That's to make 4 pair. Okay, there's only one element that breaks these rules. It's helium. What do you think the electron dot diagram for helium looks like? Okay, helium's in group 8A. Do I write 8 dots? No, because helium only has 2 electrons. So I cannot put 8 dots when there's only 2 electrons. So I've got to put 2 dots. But here's the tricky part. On helium, I put those 2 together as a pair. Say, well, why would you do that? Well, by putting them together as a pair, I'm trying to tell you something. I was forced to pair them up. It's full. Just like when these are all paired, it's full. So magnesium, they're separate because it's not full yet. Helium, they're together to let me know that they're full. So it's a pair of electrons, doesn't matter which side it goes on, but it's got to, they put them together as a pair. And it's the only exception. Right? So let's make sure everybody's on the same page. Which one of these is the correct electron dot diagram for sulfur? Okay. So, which one can we eliminate right away? D. And we could also eliminate A, because A is only 5. D was 8. And I need 6. So both B and C have 6. But B is the correct answer because C has everything paired up, which would think that we're full, yet we're not full with that one. Okay? Say, wow, I could do this for homework, right? Okay, why do we do that? Because now we can start talking about how atoms change. Okay, so last chapter, we learned about electron configurations and cations. Because remember, cations are positive, right? And the ones that form cations are metals. The reason why they form cations is to achieve noble gas electron configuration. So metals are losers. They lose electrons. They always make positive ions. Because if I lose electrons, I have the same number of positive pieces, but now fewer negative pieces. So for sodium, I would start off with 11 positive and 11 negatives. Electron configuration-wise, to be 1s2, 2s2, 2p6, 3s1. See, the biggest number in here is a 3. And the number of electrons in things that start with 3s is 1. To look like a noble gas, that electron comes off, that valence electron comes off, and then it ends up with a noble gas electron configuration. This is how we explained it last chapter. It's a pain to write those long configurations out. I mean, it even would have been a pain to do it the shorter way, that sodium is Ne3S1. So the Na plus ion would be electron configuration of neon, a noble gas electron configuration. But still, that's a lot to write. Dots make it easier. So here's how you do it with dots. So in your bell work today, you did calcium. Calcium should have had 2 dots. Okay. In fact, his metals will always have just a few valence electrons. Why? Well, where are metals on the periodic table? They're over here on the left where the group numbers are 1, 2, and 3. Right? That's why. So you're always going to have just a few, and they come off. So we draw arrows showing them leaving. And they will lose all of them. So since calcium had 2 valence electrons, and it loses both of them, you end up with a calcium with a 2+ charge. We write it as 2+ instead of +2, so we don't think it's math. That it's saying there's 2 extra positive pieces in here. It's about counting pieces, not to the second power. See? Now, when I was in high school, that wasn't the way it was written. It was written it would have been written +2. So I sometimes fall back on it because I learned it the other way. It's hard to undo habits you did for years. But I've gotten better at it. Okay? So that's what cations are going to do. So see the advantage of dots over electron configurations. That's a lot shorter, right? This is a lot shorter than the one we did with writing out the whole configuration. Okay. Last chapter, the next thing we did was the electron configurations for anions. Anions, a negative ion. And the ones that form negative ions are nonmetals. The way they form negative ions is they gain electrons. How many electrons they gain? They gain enough to look like noble gases. This should all be a review because we did this just before the last test, right? So nonmetals make negative ions, metals make positive ions. So sulfur. Group 6A, 1s2, 2s2, 2p6, 3s2, 3p4. Or I could have done neon, 3s2, 3p4. Right? Now, nonmetals are always going to have lots of valence electrons. So to look like a noble gas, there's 2 possibilities. It could lose 6 electrons, but remember what happens, that would be the 6th ionization energy. And remember, every ionization energy gets bigger. So you'd have to put a whole bunch of energy in to knock that 6th electron off, after you knock the 5th one off. That's way too much energy for it to happen. In order to look like a noble gas, the easier way for it to do is to fill up that outside energy level. So instead of being 3p4, make it 3p6. You okay with that? That was a pain. It's a lot of writing, isn't it? Let's see how much easier it is with dots. Again, nonmetals will have lots of valence electrons. So I picked phosphorus. Earlier we'd said phosphorus had 5 dots, right? There's the 5 dots, 1 pair, 3 unpaired. And it's going to gain enough electrons to fill that outer shell. So not only can you see that there's 5 dots, you can see that there are 3 holes that need to be filled. I'm missing one here, here, and here. So to make this look like a noble gas, I'd have to add 1, 2, 3 electrons. Makes sense? Because then it's got P6, S2P6, 8 valence electrons, noble gas configuration. So yeah, that's a lot shorter than writing out electron configurations. So, and we'd say that this has a 3 minus charge because it has 3 extra negative pieces that we just put in. Okay with that? So tonight's homework is going to ask you to show how these ions form. Let's try a few. Show how the following form ions. So how would aluminum form ions? So I find aluminum. It's number 13. It's group 3A. So it gets 3 dots. So I have to decide, how is this going to end up looking like a noble gas? Well, is it a metal or a nonmetal? Is aluminum a metal or a nonmetal? It's a metal, and metals are losers. So those 3 electrons are going to come off. And what I'll end up with is an aluminum with a 3 plus charge, and I'll have 3 electrons that I got to do something with. Now, those electrons aren't destroyed, they're still there, they're just not attached to aluminum anymore. So notice I showed the original one, showed what happened to the dots, and showed what it looked like when it was done, and what happened to the electrons. I get electrons out of this. What about Cl? Chlorine. Well, chlorine's a halogen. That's group 7A. So I need 7 dots. So you can look at that. Is this going to gain or lose? Gain because it's a non-metal. Gain because it only has one hole to fill. So, right, I got to put an electron in. I have to add that electron. What I make is my Cl is now full, and it's got a 1 minus or a minus charge. Notice that the electrons are on different sides. If it loses electrons, you make electrons, so you end up with them. If it gains electrons, you have to put it in. So the stuff before the arrow is what you put in, the stuff after the arrow is what you get out. See how this shows everything that happened. Electron came in, I had to put an electron in. What about carbon? So carbon gets 4 dots. So it can either lose 4, to look like the noble gas before, or it could gain 4, to look like the noble gas after it. Which one's it going to do? Well, what it tells us is which side of the zigzag line. Carbon's a non-metal. So it's going to gain. And how many will it gain? Well, it gain 1, 2, 3, 4. So I'm going to have to put in 4 electrons. So that's what I got to put in. And when I'm done on the other side, my carbon is full. And it has a 4 minus charge. You notice my charges are the same on both sides, no matter which way I do it. The top one started off at 0, ended up at 3 positives plus 3 negatives is 0. Second one started off with a negative 1, because I added that electron, ended up with a negative 1. The bottom one started off with a negative 4, ended up with a negative 4. All right, that? So what kind of electron configurations are going to be stable? Noble gas electron configurations. And the configuration of a noble gas is to have S2 and P6 filled up. S2, P6. That's a total of 8 valence electrons. And that's why they call this the octet rule, and refer to it as a stable octet. Oct for 8. Now, it's a fine point, but it's important. The octet rule is not that you end up with 8 valence electrons. The octet rule is that you end up looking like a noble gas. Because you can end up looking like a noble gas and not have 8 valence electrons. Because is hydrogen going to gain 7 electrons? No. It's you can look like a noble gas and have just 2 if you look like helium, right? So the octet rule, you're tempted to say it's going to end up with 8 valence electrons, but that's not always true. What's always true is you always end up looking like a noble gas. See the difference between those two? sometimes it gains, sometimes it loses. Oh no. So it's like those metalloids in a different way. We just never see the metal form of hydrogen very often, or ever. Okay, so now we got ions, yeah. It's a gas at this room temperature. Get it cold enough, you can get it to metal. You got to get down to almost absolute zero, though. And even then, it's tough. Okay. So now that we can make ions, now we can stick those ions together. Bond, stick to. So ions, what's going to make them stick is opposite charges. Cations have a positive charge, anions have a negative charge. That's the bond. The bond is the opposite charges sticking to each other. And things that have ionic bonds, those solids are called salts. When we talk about salt, we usually mean table salt, which is sodium hooked to chlorine. A sodium ion, which is going to be positive, hooked to a chlorine, which is negative. Okay? But that's only one kind of salt. Technically, all ionic compounds are salts. So if you look at the label, it actually says table salt. Okay. And here's some place you may have been misled in your little bit of chemistry you had before this. You were told that the smallest piece of an element was an atom, and the smallest piece of a compound was a molecule. Okay. It's not quite true. The smallest piece of an element is an atom, but the smallest piece of a compound is only sometimes a molecule. Ionic compounds don't form molecules. They form formula units. And once we figure out what a molecule really is, we'll show you that that ionic compounds don't do what a molecule really is. Actually, I don't have to go there. I can get you know. Everybody knows water. H2O. Water makes a molecule. This oxygen is hooked to that hydrogen. And if it's going to stay water, those two have to stay hooked together. You'll find that with ionic compounds, they're not specific. Any positive ion can be next to any negative ion. It doesn't have to be the one that it reacted with. That hydrogen has to stick with that oxygen when those two reacted. That makes a molecule. The fact that opposite charges are holding you together isn't specific. It's just opposite charges. So it doesn't have it's not as specific as a molecule. So they transfer electrons to look like noble gases. Once they look like noble gases, then they stick together because they have opposite charges. So the reason why the electron moves is to look like a noble gas. The reason why the compound sticks together is because they have opposite charges when that happens. So this is why they form the ions. This is why they stick together. So for salt, one of the easiest ones to explain. Na has 1 dot. Cl has 7 dots. Na is a metal. It's going to lose its one electron. Cl is a nonmetal. It's going to gain one electron. Well, where does the electron that sodium lose go to? Where does the electron that chlorine gains come from? That electron gets moved from the sodium to the chlorine. Now they both look like noble gases, except they have charges. So the electron moved, so they look like noble gases. Now they have charges. Those are opposite charges. So opposite charges attract. So they're going to stick to each other. And that's how salt forms. Now, this one was a pretty simple case because moving one electron made them both happy. Doesn't always work out that way. For example, when calcium and phosphorus react, calcium has 2 dots, phosphorus has 5. So calcium will give its 2 valence electrons to phosphorus. And that calcium will be happy. It looks like a noble gas. But the phosphorus is not happy. It still needs more valence electrons. And the only place it can get more valence electrons is from another calcium. So a second calcium comes in and gives that phosphorus another valence electron. Now the phosphorus is happy because it looks like a noble gas. But the second calcium is not happy. It still has an electron to get rid of. It's got to give that electron away, and the only thing that can take it is another phosphorus. So I have to put another phosphorus in to take that second electron. Oops. Now the second calcium's happy, but the second phosphorus is not. It needs more valence electrons. The only place it can get more valence electrons is from another calcium. Is this ever going to end? Well, yeah, it ends right here. Because when those two move, everybody's happy. The calciums all look like the noble gas before. They all look like argon. The phosphorus all look like argon. So I got my noble gas configuration. Everything looks right. And this will stick together. And this is a place where we can talk about why it's not a molecule. This calcium lost 2 electrons. Can you tell which phosphorus it lost them to? Does it matter? No. That's why it's not a molecule. I mean, because when I do the water one, it won't let me write for some reason. So I think about water. That hydrogen has got to be hooked to that oxygen. We know those two interacted. We don't know which phosphorus this calcium gave its electrons to, and it doesn't matter. That's the difference between a molecule and a formula unit. And the formula unit for this would mean that I'd have 3 calciums and 2 phosphoruses. So it'd be Ca3, P2. And we can figure that out just by following the dots. Okay? So it really is just the first 2 things we did put together. Except everybody's got to end up looking like a noble gas. So let's try Mg and Cl. Show how Mg and Cl would make an ionic compound and tell me what the formula is going to be when you're done. Well, Mg gets 2 dots. Cl Halogen gets 7 dots. So magnesium can give 1 to chlorine, but then that chlorine's done. Magnesium still has another 1 to get rid of. So I'm going to need another chlorine. So when I'm done, I've got a magnesium that's 2 plus. And 2 Cls that are both 1 minus. So my formula is going to be MgCl2. Yeah. Oh, the charge, no, I did. I put the charge. Because 2 plus, 1 minus and 1 minus adds up to 0. So the compound doesn't have a charge. Because we made sure all the electrons were accounted for. Because magnesium lost 2 electrons, chlorine gained 2 electrons, we're still talking about the same number of electrons. Okay? So that's what I'll have you do on tonight's homework. Okay? Have a great day.